So now in section 5.3, the main concept that we'll be talking about is called the diagonalization of a matrix. Okay, we want to diagonalize the given matrix. Now you may raise the question, what is the use of diagonalization? Why do we want to diagonalize? Let's look at one simple example. Okay, let's say you are given a matrix A, which is 2, 0, 0, 4. Okay, I want you to calculate find A cube, let's say. How do you do that? One way is to write, because A cube means A times A cube means A times A times A, right? So A is 2004 times 2004 times 2004. Now you multiply this first two. Okay, guys, multiply the first two, let me know, and then we'll multiply the last one later. This will be 4, 0, 0, and 16. If I'm wrong, let me know. Did you get the same thing?
Yes, Professor.
Yeah. Okay, now let us multiply these two. So you're going to get 8, 0, 0, and 64. Let me know if I'm wrong. This is correct. Okay, so this one I can write this guy as 2 cube, 0, 0, and 4 cube, right? Now, you see, notice that if A is 2004, it's a diagonal matrix. Then if A is diagonal, which is 2004, then A cube will be simply 2 cube, 4 cube, right? It's that simple. You don't have to do all of these now. Now, if I ask you, okay, A is this, and if I ask you A raised to power 300, how much is that? Well, you can tell me right away. You don't have to do all these multiplication now. You can tell me A power 300 will be 2 power 300, 0, 0, 4 power 300. It's that simple. So if somehow we can, if we have a diagonal matrix, then, you know, finding A cube or A raised to power 30 or A power 100 or 1000, whatever, then we can calculate easily. If it is not diagonal, then we have to follow this method. Suppose B is, let's say 1, 2, 3, 4, for example. If I ask you what is B raised to power 300, so until now, what we need to do is we need to write all these 300 terms. B means 1, 2, 3, 4, and then 1, 2, 3, 4, and write all the way up to 300 terms, and you multiply them all. It's not fun. I'm telling you, it's not fun. It takes a lot of time, maybe the whole morning or whole day, and you don't want to do that. So somehow, if we can change this matrix B into a diagonal matrix, then we can find it easily, right? That's the power. That's the beauty of diagonalization. And that's what we're going to learn now. All right. So here, example B, A is 2, 1, 2, 3. This is not a diagonal matrix. And if you want to calculate A raised to power 2014, you know, until now, what you need to do is you need to, you know, multiply this matrix 2014 times. That's too much. But in today's class, we will learn a technique we will learn a technique how we can diagonalize the given matrix so that we can, we can find it easily without any difficulty. Now the question is, how can we do that? What is the process? First of all, let us define what this diagonalization means. A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix, that is, if A equals PDP inverse. Okay, if A is not a diagonal matrix, we will find another matrix which is equal to A, but this matrix will be a diagonal matrix. Okay, that's what we're going to do. So theorem 5, the diagonalization theorem. If n by n matrix A is diagonalizable, if and only if A has n linearly independent eigenvectors. So when is matrix A diagonalizable? If A has n linearly independent eigenvectors. Okay, notice that. N and n linearly independent eigenvectors. Now, here are the steps. We're going to follow this step 1. You can read that by yourself. I think just by reading this step may not make sense. Step 1, step 2, step 3, step 4, step 5. These are the 5 steps we need to follow in order to diagonalize a matrix. Now, let me show you with example. Just reading the step may be confusing. So let's work with the example. Diagonalize A if possible, where A is given by this matrix. Clearly A is not diagonal, right? A is not a diagonal matrix. So step 1, we find the eigenvalues of A. That means we write the characteristics equation. Okay, guys, please write the characteristics equation. So what is A minus lambda I first? Let me just calculate that. A minus lambda I is A is 300, negative 349,003 minus lambda I is 100,010,001, or I can okay, yeah, this one. And if you work it out, so you're gonna get 3 minus lambda 0, negative 3, 4 minus lambda 9, 0, 0, 3 minus lambda. Okay, so eigenvalue. So characteristics equation is, I simply write CH for characteristics. Okay, in short, characteristics equation is determinant of A minus lambda I equals 0, which means determinant of this matrix 3 minus lambda 0, 0, negative 3, 4 minus lambda 9, 0, 0, 3 minus lambda equals 0. Now we need to find the determinant of this. So which row or column do you want to expand?
First row.
Expanding. Maybe let's expand the first row because there are 2 zeros. So expanding first row, recall from chapter 3. So you're going to get 3 minus lambda, and then the remaining is, this is gone, this is gone. So this is gone, this is gone. Okay. So you're left with negative 3, no, sorry, 4 minus lambda, 4 minus lambda and 9, and there 0 and 3 minus lambda equals 0. So 3 minus lambda, and then this will be 4 minus lambda times 3 minus lambda minus 0 equal to 0. Oh, basically you got 3 minus lambda square and 4 minus lambda equals 0, right? Now, what are the eigenvalues?
3 and
Yes, eigenvalues are with algebraic multiplicity R is given by lambda equals 3, algebraic multiplicity is 2, lambda equals 4, algebraic multiplicity is 1. Is there any question so far?
No.
Okay. Step 1 is done. Now let's go back. What is in step 2? In step 2, if possible, find basis for each eigenvalues. And this is what we call eigenspace, by the way. We need to find eigenspace, meaning we need to find the basis for the eigenspace, okay? So how do we do that? To find basis for eigenspace corresponding to lambda equals 3, because we need to, here we have lambda equals to 3 and lambda equal to 4. So let us find the basis for eigenspace for each of these lambda value. So for lambda equals to 3, to find the basis for eigenspace corresponding to lambda equal to 3, what we do is recall from the previous section that if 3 is eigenvalue, you know the definition, lambda x ax equals lambda x, right? That's the definition of eigenvector. If
Yes.
lambda equals to 3, then by definition we can write, ax equals lambda x, which gives me ax equals 3x, which gives me a minus 3x equals 0. But since A is a matrix, in order for this to be defined, I'll write 3i, x equal to 0. Now our job is to solve this system. I think we have done that in our last class as well. It's pretty much the same thing. So now we need to solve this system of equation, for which consider the augmented matrix A minus 3i and 0. Okay, and we have augmented matrix, we change it into echelon form, and then we'll get the basis. So that means A minus 3i. Okay, what is A minus 3i? Let us figure that out.
0, 0, 0.
Okay, 0, 0, 0.
Minus 3, 1 and 0.
Minus 3, 1 and 0.
Yeah. No, it's 9, 9.
Okay.
Yeah.
The
Then
third,
again 0, 0, 0.
thank you. Everybody got that? And then 0 means 0, 0, 0 on this side. So this is our augmented matrix. Now, I would like you to change this into echelon form. Change to echelon form, which
We
is
just need to.
right? You just you just row interchange the row, and then you will be done. You will have echelon form. So I'll do this -3 1 9 0 and 0 0 0 0 0 0 0 0. Okay, this is in echelon form. Now we'll write the what are the basic variable and what are the free variable. So
x1 is basic variable and x2 and x3 are free.
exactly. So let us write the general solution then. So general solution will be -3x1 plus x2 plus 9x3 equals 0, and x2 and x3 free. So from this one we can get x1 will be, if I solve it, I'll get 1 over 3 x2 plus 3x3. Am I right? Okay, we got that. So let me write that in a nice form. General solution in the nice form is x1, x2, x3, which is x1 means 1/3 of x2 plus 3x3 and x2 and x3. So x2 plus x3. So you can get the vector right away. So this will give me 1 over 3, 1, 0, and this will be 3, 0, 1. Right? So the basis for eigenspace corresponding to lambda equals 3 is 1 over 3, 1, 0, and 3, 0, 1. Okay. So, and these basis vector are called the, determines the geometric multiplicity. So in this case, lambda equals 3, the geometric multiplicity is 2 because there are two vectors. Okay, there are two basis vector. So note that geometric multiplicity is given by the number of basis vector. Geometric multiplicity equals, well, yeah, given by the number of basis vector of the eigenspace corresponding to the eigenvalue. Okay, this is the definition of geometric multiplicity. You don't need to write this down here. I'm just letting you know that this is the this is called the geometric multiplicity. So the geometric multiplicity of lambda equals 3, you can simply write, so geometric multiplicity for lambda equals 3 is 2. Okay, because there are two vectors. Okay, so we are done with lambda equals 3. We need to do the same step, same process for lambda equals, what is the another eigenvalue, by the way? Another eigenvalue is lambda.
Professor,
Yes.
I don't get how we got this geometric multiplicity for lambda.
Okay. This one is basis vector. So how many vectors are there?
2.
Okay, so geometric multiplicity is 2. This is
Okay.
number of vectors here. Number of basis vector is called the geometric multiplicity.
Okay.
This is for eigenspace. Okay. Now let's look at the geometric multiplicity or basis for lambda equals 4. The same method. Now for lambda equals 4, we want to find the basis vector. For lambda equals 4, we find basis for eigenspace corresponding to 4. Okay. Now again, for this, by definition, ax equals lambda x, which gives me ax equals 4x, because lambda is 4 for this second value for lambda. This gives me a minus 4i x equals 0. Right? Now we need to solve this system. Now to solve this system of equation, consider augmented matrix. A minus 4i and 0, which is a minus 4i. Can you tell me what is a minus 4i will be? Somebody help me.
-100 -309
Thank you.
and 00 -1.
Okay, good. I want to verify that with other people. Everyone got that? The same?
Yeah.
Okay, good. So if you get the same thing, then that means it must be the correct one, right? It's very difficult to get the same wrong answer. We know that. Okay, so now let us change it into echelon form. Change to echelon form. And let me know. Did you get the same thing?
Yes, Professor.
Or you can write this one if you like. You can write, instead of 9, you can take 9 common, and you can write 1 if you like. No problem. Okay, so let us write the general solution then. Let me write here. General solution will be negative x1 equal to 0, and then x3 equal to 0. And what is free? x2 free. Okay, so let me write this in a nice form. If negative x1 equal to 0, that means x1 is also 0. So x equals, we have x1, x2, x3. x1 means x1 is 0, x2 is free, and x3 is also 0, right? So what I can write here is that 0, 1, 0, right? So this is the basis for eigenspace, basis vector for eigenspace corresponding to lambda equals 4 is given by this vector 0, 1, 0 only. So what is the geometric multiplicity? How many vectors, basis vectors are there?
1.
Yes, so geometric multiplicity of lambda equals 4 is 1, because there is only one vector in the only one basis vector. Okay, any questions so far?
No, Professor.
Now let me ask you one thing. What was the algebraical multiplicity of lambda equals 4? We did that in step 1. What was the algebraic multiplicity?
It's 1.
1. Okay. Now let me ask you another. What was the algebraic multiplicity for lambda equals 3 in step 1?
It's 2.
Okay. So now my question is it always true that geometric multiplicity and algebraic multiplicity are equal? What is your thought? What is your guess, I would say? Is it a coincidence or it is always the case?
Maybe it's always the case.
Any other idea? By the way, this is not always the case, okay? If the geometric multiplicity and algebraic multiplicity are equal, then that matrix can be diagonalized. We can find the diagonal matrix. If the geometric multiplicity and algebraic multiplicity are not equal, then we cannot diagonalize. So suppose if we got that, the geometric multiplicity for 3, lambda equal 3 is 1, then we will stop here. We don't have to do any other stuff. We just say that it is not diagonalizable. Okay, so the matrix will be diagonalizable only if algebraic multiplicity equals geometric multiplicity. So keep that in mind. Now, construct P and D so that A equals, we need to find a similar matrix now, okay? Construct P and D so that A equals PDP inverse, where P is B1, B2, Vn. Okay, what is B1, B2? B1, B2 is this, and V3 is all the way here. This is our V3, the basis vector. This is our V3. Now, let us construct P. So P is given by those vectors B1, B2, B3, okay? Basis vector B1, B2, B3, which is 1 over 3, 1 and 0, 3, 0, 1, and then what is the other one? 0, 1, 0, 0, 1, 0. So this matrix is called P matrix. Okay, P is this. Now we need to construct D as well. D matrix. What is D matrix? The D matrix is a diagonal matrix whose diagonal entries are the eigenvalues. So it means lambda 1, lambda 2, lambda 3, and here 0, 0, 0, 0, 0, 0. So this is called D matrix. Now, what is our first lambda? 3. What is our second lambda? Again 3, because there are 3 factors we saw in step 1. Okay, the 3 has 2 algebraic multiplicity, so you need to write 3 twice, and 4 has only 1 multiplicity. So this is D. P, this one is P, this one is D. That's how we create. Do you have any question how to create the matrix P and D?
Professor?
Yes.
Is it not matters like which value we give to lambda 1, lambda 2, and lambda 3?
It matters because you see the first V1 and V2 is for 3. So therefore I write 3 first. Okay. Here I write V1, V2 first and then 3, 3. But if you want to write, let's say, or you can write this way as well. Suppose you want to write this V3 first, for example. You want to write 0, 1, 0, 3, 0, 1 and 1 over 3, 1, 0. If you want to write your P matrix this way, then your D matrix will be, remember, the first vector is for which eigenvalue?
It's for 4.
Okay, you must write 4 first.
Okay.
And then 3, 3. So either you can write this way or you can write this way. Okay, the vectors, the basis vectors and the eigenvalue, they will go together. So if you write v1 as your basis for lambda equals 4, then you must write, this one is for lambda equal to 4, this is 4. The second vector is for lambda equal to 3, so lambda equal to 3, and so on. Make sense?
Yes.
Okay, now we are done. So we found a matrix A, which is given by PDP inverse, where P is this matrix, D is this, or if you consider P as this and D as this one. Now let us check whether it actually works or not. Okay, so remember, if A equals PDP inverse, then multiplying by P inverse both sides, then you can write AP equals PD, right? From this one, if you do a little bit of algebra, then they should be equal. Let us check whether this is true or not. I want you to calculate what is AP, and I want you to calculate what is PD. So let us calculate this just for fun. You don't have to show this in your exam unless the question asks you to check your answer. But right now, let's try it just for fun. AP. So A is, what is that A matrix? 3, 0, 0, negative 3, 4, 9, 0, 0, 3. Did I copy the right matrix there, A?
Yes, Professor.
Okay, P. Let us copy that P. The P matrix is the matrix that we created. 1 over 3, 1, 0, 3, 0, 1, 0, 1, 0. Please calculate this. And also calculate PD. P is 1 over 3, 1, 0, 3, 0, 1, 0, 1, 0. And then D is, okay, what is D? 3, 0, 0. For this one, okay, this vector is for lambda equal 3. Yes, 3, 0, 0, 0, 3, 0, 0, 0, 4. I want you to find this and check whether they are equal or not. If they are equal, then your answer is correct, our process is correct. If they are not equal, then we need to go back and check where we made a mistake, okay? Okay, so when we multiply A and P, these two matrix, then we got 190, 304, 030. And here also PD is 190, 304, 030. Okay, so that means our answer is correct. All right. What it means is A equals PDP inverse. So that means A can be written as your matrix A, which is, again, what is that matrix A? A is 3, 0. Okay, A is 3, 0, 0, negative 3, 4, 9, 0, 0, 3. This matrix can be written as P, which is 1 over 3, 1, 0, 3, 0, 1, 0, 1, 0, P, and then D is this matrix 3, 0, 0, 0, 3, 0, 0, 0, 4, and then P inverse, you can calculate that P inverse yourself. And so this matrix and the product of these three matrices will be equal. That's what it means. Like I said earlier, a couple of things to keep in mind is that the algebraic multiplicity of an eigenvalue is greater or equal to its geometric multiplicity. If for each of the eigenvalues, the algebraic multiplicity equals the geometric multiplicity, then the matrix is diagonalizable. Otherwise, we call the matrix is defective. Okay? If algebraic multiplicity equals geometric multiplicity, then we can diagonalize. But if algebraic multiplicity is not equal to geometric multiplicity, then we cannot diagonalize that matrix, and we call it defective matrix. Okay, defective matrix. All right, now let's try this example 2 very quick. Step 1. Please find the eigenvalues for this, guys. So this is it's a good news, right? This is a triangular matrix. Okay, good. You identify that already. All right. So since A is a triangular matrix, eigenvalues are lambda equals 1 and algebraic multiplicity. How many 1 are there in the diagonal?
2.
2. So algebraic multiplicity 2 and lambda equals 2 and algebraic multiplicity is 1, right? Okay, step 1 is done. Now step 2, we need to find a basis for the eigenspace. Okay, so to find basis for eigenspace, let's consider lambda equals, okay, for lambda equals 1, let's consider this first. Okay guys, you already know how to do this. Go ahead and try that. By definition, ax equals lambda x. This gives me ax equals lambda is 1x, which gives me a minus 1i, which means simply I, x equal to 0. To solve the system, consider augmented matrix a minus I and 0, which is okay. Somebody help me. What is a minus I?
It's 0, 3, 5.
0, 3, 5, and then
0, 0, 1. And again 0, 0, 1.
Thank you so much. Okay, now change it into echelon form.
For that, we just get 0, 3, 5, 0, 0, 1, and the last row is 0, 0, 0.
Oh, it's so quick. Thank you. So in echelon form, you will be getting 0, 3, 5, and 0, and 0, 0, 1, and 0, 0, 0, 1. Is that right?
No, it's 0.
It's 0. Okay, thank you. All right. So let's see. General solution. 0x1 plus 3x2 plus 5x3 equal to 0. And from the second one, we have x3 equal to 0. And what is free?
x1.
Free. Okay. So now we need to change this. X1 is free means, okay, 3x2 plus 5x3, x3 is 0, so let me substitute the value. Okay, this, if I substitute the value 0 there, and that's gonna give me x2 is also 0, right? So the general solution is actually x is x1, x2, x3, which is x1 is 0, x2, oh, x1 is free. We have just right, x1 is free, x2 is 0, x3 is 0. So basically what we got here is 1, 0, 0. So the basis for eigenspace corresponding to lambda equals 1 is 1, 0, 0. And so geometric multiplicity is
Also 1.
1. Okay, so now good news. This matrix is defective. You know why?
Because algebraical multiplicity is 2 for 1.
Excellent. Okay, since algebraic multiplicity is not equal to geometric multiplicity, matrix A is not diagonalizable. Matrix A is not diagonalizable. Done. You don't have to do the other one. Okay. Any question, guys?